The Second World War stands as the crucible of modern aviation, a conflict where the design, speed, and power of the aerial machine evolved at a staggering, almost impossible pace. The war began with biplanes and simple monoplanes, but by its conclusion, the thunderous promise of the jet age was already whispering on the horizon. Yet, before the final, decisive transition to jet propulsion, there was a relentless, feverish race to extract every last fraction of performance from the piston engine. In the final, desperate years of World War II, engineers, particularly those in the United States, unburdened by the immediate threat of bombing, pushed piston technology to its absolute, screaming limits. They experimented with massive superchargers, multi-stage turbo units, high-octane fuels, and engine blocks so complex they were engineering marvels in themselves. The goal was simple, yet profound: create the fastest, highest-flying interceptor possible to dominate the thinning skies of Europe and the vast spaces of the Pacific. And from that frantic, pressure cooker environment of innovation emerged a machine so fast, so powerful, and so unique in its engineering solutions that it would ascend to an almost mythological status. It was the absolute, unassailable apex of the propeller-driven era, the final, glorious chapter before the jet plume took over. It would become, by the end of its development, the fastest piston engine fighter the world had ever seen. This machine was a testament to American industrial might and the sheer, uncompromising audacity of a small group of design visionaries. It was a fighter designed to shatter existing speed records, to fly at altitudes previously reserved for specialized bombers, and to carry a payload of firepower few other single-engine aircraft could manage. It was destined to be a legend, a benchmark against which all propeller planes would forever be measured. But what history often forgets, what is frequently obscured by the plane's spectacular performance records and its unique, imposing profile, is the simple, devastating truth: it almost never left the drawing board. The story of this aircraft is not just a story of engineering triumph, it is a story of bureaucratic warfare, intellectual resistance, and the crushing inertia of institutional skepticism. It is the story of how a radical, future-defining design nearly died, smothered by caution and dismissed as an extravagant impossibility. Its existence was a profound counterpoint to the established wisdom of the time, and therefore, its champions had to fight not just physics, but the very system that funded and fought the war. The very audacity of the design was its primary threat. It challenged everything the military procurement systems believed to be prudent, necessary, and achievable in wartime. The project that would yield the world's fastest fighter began with a specific, yet staggering, technical requirement: the need for an interceptor capable of operating effectively at extreme altitudes, well over 30,000 feet, to counter the threat of high-flying enemy reconnaissance and, eventually, specialized bombers. When the design team, led by a small coterie of visionary engineers, submitted their proposal, it was met not with enthusiasm, but with an immediate, overwhelming wave of skepticism. Military officials, men schooled in the conservative design principles of reliable, mass-producible aircraft like the P-47 Thunderbolt and the P-51 Mustang, dismissed the proposal as unrealistic, impractical, and, frankly, dangerous. The reasons for this deep-seated institutional disbelief were rooted in the very radical nature of the proposed engineering. 1. The engine. The massive heart of the problem. The core of the design demanded a massive, experimental engine, a gigantic, complex power plant that pushed the boundaries of metallurgical and mechanical tolerance. It was likely a high-compression, water-cooled V-engine of enormous displacement, requiring vast amounts of high-octane fuel and a gargantuan, complex supercharger and intercooler system to force-feed air into the cylinders at high altitude. This engine represented a massive leap over existing, proven wartime engines. It was heavy, untested in operational conditions, and required specialized tooling and maintenance, a logistical headache in a global war. 2. The cooling system. A radical, risk-laden solution. To achieve the desired speed, the design minimized aerodynamic drag to an unprecedented degree. This meant eliminating the traditional drag-inducing radiators found on wing and fuselage surfaces. Instead, the aircraft proposed an experimental cooling system, a ducted radiator or perhaps even an early, integrated surface cooling solution. While brilliant in theory for reducing drag, this system was highly complex, extremely vulnerable to battle damage, and had a known propensity to overheat during stress tests. It was a trade-off of speed for reliability, a frightening prospect for pilots flying deep into enemy territory. 3. The airframe. The impossible shape. The radical airframe was unlike anything produced in mass numbers. To cope with the massive torque of the engine and the unprecedented speeds, the airframe had to be engineered with incredibly tight tolerances and use advanced, high-strength alloys. It required specialized manufacturing techniques, demanding far more labor and much higher-grade materials than the war effort could easily spare. It was sleek, but utterly unforgiving in its demands on the factory floor. The verdict of the committee. The officials of the procurement committee, faced with a proven war machine churning out thousands of reliable planes, saw the new design not as an opportunity, but as a wasteful, unnecessary risk. Their final report was a damning condemnation. Too big, too expensive, too risky, one report concluded, citing concerns over development time, manufacturing complexity, and the potential diversion of scarce resources, specifically the high-powered engines, away from existing, successful programs. This wasn't simply a matter of bad taste, it was a fundamental clash of philosophies. The committee prioritized quantity and reliability for the immediate needs of the war. The designers prioritized and compromised speed and ultimate technological supremacy for the potential needs of tomorrow. In the pragmatic, bloody context of World War II, caution often won. For a chilling moment in time, the project was stalled. The proposal sat gathering dust in a committee office, its budget frozen, its engineers assigned to less ambitious modifications of existing planes. The fastest fighter in history, the technological pinnacle of its era, nearly died in committee, suffocated by bureaucracy, budget constraints, and the cold, hard logic of wartime necessity. The visionaries were told to go back and design a better P-51, not a revolutionary piston-age hyperfighter. The fight to build the plane had just begun, and it was a battle fought not with guns, but with blueprints and budget memos. While the ambitious design for the ultimate piston fighter lay dormant, mired in the bureaucratic quicksand of procurement committees and cost-benefit analysis, the brutal, unrelenting realities of the war in the air were undergoing a profound and terrifying shift. The simple, conservative logic that had initially doomed the project, the focus on reliable mass production, was rapidly becoming obsolete. The enemy, driven by desperation and their own brilliant, if often resource-constrained, engineers, was relentlessly raising the bar. The skies of both the European and Pacific theaters were witnessing a sudden and dangerous surge in enemy performance. Enemy fighters were becoming faster, deadlier, and more heavily armed. This wasn't a gradual improvement, it was a technological sprint born of necessity. In the Pacific, the later model Japanese aircraft, such as the formidable Kawanishi N-1K Shidenkai, George, or the improved variants of the Mitsubishi A6M0, had finally begun to address the shortcomings of earlier Japanese designs, primarily their fragility and low diving speeds. They were heavier, sturdier, and packed with serious firepower, forcing American pilots to fight harder and risk more just to maintain aerial parity. More critically, in Europe, the American bombing campaigns were facing new, sinister challenges. The Germans, fighting a desperate war of defense, were introducing high-performance, piston-powered interceptors like the Dornier Do 335 File Arrow, and later versions of the Focke-Wulf FW-190 that could meet Allied fighters at higher altitudes and greater speeds than before. Even more ominously, the Germans were already deploying early, terrifying jet-powered aircraft, such as the Messerschmitt Me-260. Archival footage of Me-262. The intelligence reports landing on the desks of Allied commanders painted a grim picture. Existing American aircraft struggled to keep up at high altitude. The venerable P-51 Mustang, the workhorse of the European theater, was a masterpiece, but even its superb performance began to degrade significantly above 30,000 feet, where the air was thin and the enemy was increasingly operating. The heavy P-47 Thunderbolt, while a superb high-altitude platform, was approaching the limits of its power plant and airframe design. The war had suddenly created a performance gap. American bombers, now flying deeper into the Reich than ever before, were increasingly vulnerable to these advanced German designs, particularly the Schwalbe Swallow jets, whose sheer speed rendered conventional escort tactics obsolete. The need was simple. America required an interceptor that could fly higher, fly faster, and sustain that performance longer than anything currently in the inventory. It needed a piston-engined plane that could push past 450 miles per hour and climb with an unprecedented rate, a plane that could be ready now, before jet production ramped up. The strategic conversation shifted from, "Can we afford this risk?" 2. Can we afford not to take this risk? Suddenly, that impossible design, the aircraft that demanded a massive engine, experimental cooling, and a radical airframe, didn't look so impossible, it looked absolutely necessary. The very flaws that had caused its dismissal, its over-engineered power, its hyper-optimized streamlining, were now its primary selling points. The committee's initial caution had almost cost the Allies their aerial superiority. In a moment of strategic desperation, driven by the mounting losses of bombers and the fear of losing the technological edge, commanders revisited the abandoned proposal. The blueprints, pulled from dusty storage files, were suddenly illuminated under the harsh light of wartime urgency. The engineers who had been ridiculed were now summoned back to the table, their complex equations and daring assumptions suddenly validated by the cold statistics of combat losses. The new directive was absolute: give it a second chance. The bureaucratic blockade was lifted, replaced by an urgent, wartime mandate. The program was pulled out of the normal procurement cycle and given a black project designation, bypassing typical oversight and funneling vast resources into its development. The race was now on, not against a committee, but against the relentless advance of German technology and the ticking clock of the war itself. The time for caution was over, the time for speed, at any cost, had arrived. Securing the funding and the mandate was one battle, turning the radical concept into a working, flying aircraft was a nightmare of physics and manufacturing stress. The engineers and mechanics who had championed the design now faced the immense, terrifying task of making the impossible function reliably under operational conditions. The development phase was a constant, grueling battle against fundamental mechanical and aerodynamic forces. The initial prototypes were temperamental, dangerous, and often spent more time in the hangar than in the sky. The engine's revolt. The core problem remained the massive, high-performance engine. It was an engineering marvel, capable of delivering power output that dwarfed its contemporaries, but it was incredibly sensitive to heat and stress. The overheating crisis. The experimental cooling system, designed to minimize drag, was constantly on the verge of failure. During sustained high-power runs, the engine would violently overheat. Mechanics repeatedly watched as oil pressure dropped precipitously and engine components glowed red. Engineers had to reinvent the cooling ducts multiple times, adjusting the complex airflow systems to draw maximum heat away while still preserving the razor-thin aerodynamic profile. The margin for error was non-existent. Propeller system failure. The sheer torque generated by the massive engine at high RPMs was a perpetual threat to the propeller system itself. The complex reduction gearboxes, which transferred the engine's tremendous power to the propeller, repeatedly failed, fractured, and seized. They had to be continuously redesigned, strengthened with new alloys, and tested until they could reliably handle the gargantuan forces involved. Prototypes shaking themselves apart. When the aircraft finally took to the air, new problems emerged, defined by the unprecedented speeds it achieved. Structural instability. Early prototypes, during high-speed dives intended to simulate combat maneuvers, would literally shake themselves apart. Control surfaces fluttered violently, wings twisted, and rivets popped out like seeds. The airframe, though designed for high strength, was being subjected to forces that existing engineering calculations simply hadn't fully accounted for. This demanded extensive redesigns of the wing spar structure and the use of even rarer, higher-grade aluminum alloys, slowing production further. Compressibility issues. As the fighter approached speeds near Mach 0.8, close to the speed of sound, it began to encounter compressibility effects, where air stops flowing smoothly over the control surfaces. The stick would lock up, and the aircraft would become dangerously uncontrollable. The engineers were forced to delve into aerodynamic theory that was barely understood at the time, leading to radical design changes like the addition of dive brakes or redesigned wing leading edges to mitigate these crippling effects. The entire process was characterized by a frantic pace, fueled by the ticking clock of the war. Every hour mattered. The engineers and mechanics, working around the clock in secretive test facilities, were constantly adjusting overheating parts, stripping failed gearboxes, and redesigning structural joints. They knew that the war was a finite event. It might have ended before the plane was truly ready for operational deployment. The pressure was immense. The plane's failure would not just be an embarrassment, it would be a strategic calamity, leaving the crucial high-altitude bomber formations exposed. The project became a living manifestation of the absolute limits of piston engine technology, a screaming, metal-stressed attempt to defeat the laws of physics, all in a desperate race against time. The long, grueling ordeal of development, the engine failures, the structural shudders, the constant battle against heat and drag, had led to a singular, defining moment. The engineers, exhausted but hopeful, had incrementally conquered the most pressing problems. They had reinforced the wing spars, perfected the tricky ducted cooling system, and, most crucially, tamed the monstrous power plant. All the stress, the doubt, and the immense financial gamble hinged on one test flight, the moment the prototype was pushed beyond the known limits of piston engine aviation. The day of the final, decisive high-performance test was tense. At the secured air base, the atmosphere was heavy with anticipation. A small group of senior military officers and the exhausted design team stood clustered near the hangar, watching the lone figure of the test pilot climbing into the cramped cockpit. This wasn't a standard flight. This was an attempt to validate the entire premise of the program, to deliver the speed that had been promised and demanded. The aircraft itself, with its massive nose housing the enormous engine and its sleek, tightly cowled fuselage, looked less like a conventional fighter and more like a bullet with wings. It taxied out, its engine perhaps a high-output variant of the Allison or Packard V-12, growling a deep, guttural sound unlike the higher pitch of smaller fighters. The takeoff was rapid and smooth, a testament to the sheer thrust of the engine. Then, the test profile began, an aggressive, sustained climb meant to demonstrate the aircraft's ability to intercept high-altitude threats. The aircraft climbed higher, accelerated faster, and clawed its way through the thin air more effectively than any Piston fighter before it. At 35,000 feet, an altitude where other fighters were struggling for breath, this machine was still accelerating, its supercharger system performing flawlessly, forcing dense air into the engine. The tension on the ground was palpable, but the real data was being recorded miles away. At the remote radar and telemetry stations, the readings coming in were shattering all existing benchmarks. The radar crews couldn't believe the speed readings. They double-checked their calibration, assuming instrument error. The recorded velocity at altitude was not just faster than the P-51, it was a quantum leap beyond it, pushing toward speeds that were theoretically impossible for a propeller-driven aircraft in level flight. The plane then executed the final, most terrifying part of the test, a full-power, high-speed dive. This was the moment where earlier prototypes had failed, where the airframe had shivered itself to destruction. The pilot pushed the nose down, and the huge machine fell toward the earth, the propeller tips approaching the speed of sound. The airframe held. The controls, though heavy, remained responsive. The speed indicator pegged itself at a velocity that put the plane squarely in the realm of compressibility, a territory that had claimed the lives of previous test pilots. The plane survived the dive, pulling out cleanly and demonstrating its structural integrity. When the pilot, weary but exhilarated, finally brought the prototype down for a perfect landing, the anxious engineers rushed the plane. They didn't need to ask for the data. The look on the pilot's face told them everything. His simple, now legendary debriefing line summed up the entire journey from design concept to mechanical reality: it wants to go faster. The impossible plane had finally come to life. The engineering masterpiece, the bureaucratic headache, the desperate gamble, it had paid off. The world had nothing else like it. The Axis powers had nothing that could touch it at its operational altitude. The Allied High Command now possessed the ultimate Piston interceptor, a weapon that could not only counter the advanced German designs but completely dominate the air war until the jet fighters became numerous enough to take over. The speed gap was closed, and then some. The price had been high, the road fraught with peril, but the engineers had successfully pushed Piston technology past its supposed physical limits. The triumph of the ultimate Piston fighter was absolute, but the timing was tragically ironic. The aircraft, having defied doubts, survived committee hearings, and overcome the very laws of physics, finally entered limited service just as the war was reaching its climax. It served as a high-altitude interceptor and photo reconnaissance platform, performing missions with an ease and speed its predecessors could only dream of. In the brief window it was operational, it proved its performance superiority, demonstrating the potential for total air dominance against any remaining propeller-driven threat. However, even as the first operational squadrons were being formed, the true harbinger of the future was already casting its shadow. The jet age had arrived almost immediately. The German Me-262, the very aircraft that had, in part, motivated the desperate creation of the world's fastest piston fighter, had introduced an entirely new dimension to air warfare. While the American plane was hitting speeds of over 470 miles per hour, approximately 756 kilometers per hour, the jets were capable of speeds exceeding 540 miles per hour, 870 kilometers per hour. The piston engine, no matter how ingeniously supercharged and streamlined, had reached a fundamental, unbreakable barrier: the efficiency and speed of the jet turbine. The plane that represented the absolute zenith of piston engine technology was, ironically, born just as the world was decisively preparing to leave piston engines behind. The long, frustrating delays in procurement and development, the very bureaucratic inertia that had almost killed the project in Part 2, meant that when the plane was finally ready, its strategic lifespan was measured not in years, but in months. As the war ended, the massive production lines stopped. The need for the ultimate propeller plane vanished overnight, replaced by the immediate imperative to develop and mass-produce jets. The resources that had been poured into perfecting its hyper-complex engine and airframe were now diverted to the simplicity of the early jet engine. The world's fastest piston engine fighter never got the chance to reshape the war as its designers had intended. Its combat career was short, its numbers few. Yet its legacy remains. It sits today in museum exhibits, a towering, unique presence among its wartime brethren. It is an engineering masterpiece that defied doubts, deadlines, and the previously accepted limits of aerodynamics and physics. It represents a watershed moment, the definitive answer to the question, how fast can a propeller plane possibly go? It stands as a testament to the unyielding spirit of innovation, proving what piston technology, driven by necessity and the genius of its creators, was truly capable of. It is the story of a design that was too radical for its time, but ultimately too brilliant to fail, a fighter that shouldn't exist, but which, by existing, became an unforgettable piece of aviation history. The bureaucratic blockade could slow it down, but it could not stop the inevitable march of technical genius.